Hey, welcome. So I know it's late in the conference and this is a scary topic, threat intelligence. Well, I hope we'll make it a little bit entertaining. We'll have an untested special effect. So first of all, I guess most of you, I think many of you are in the scene and have been for a while. And I think we can say cloud native security, in a sense, has come a long, long way since Kubernetes started. However, if I also talked with you, many of you, during these 2 days, out there in the wild with the companies and customers, security often is still a bit of an afterthought, especially when it comes into threat intelligence. And here, one reason I see is that the thing that makes cloud native and the community great is that standing on the shoulders of giants, right? That we can build upon each other. And this is something that I think in threat intelligence especially, we just don't have a standard to share. We don't have a framework to share. So for example, if I find something to be exploitable, maybe I'm writing a POC, or if I see on my cluster something is being exploited, there's not really any means for me to share this with someone else without them having to understand the entire context of my cluster. And this is why back in KubeCon Paris, we introduced this idea of the Kubernetes Storm Center, slightly modeled on the SANS Storm Center of basically figuring out what's currently going on in the cloud native scene in a shareable way. So this is to be a method and a framework of, on the one hand side, understanding if my threat modeling is accurate, and on the other side as well, especially with having maybe stuff like NIS2 in the back of the mind, is like, if I had a simulated breach, is my detection and response actually in place? Does it actually work, like hands-on? And well, you might have noticed that I'm not alone here. So my name is Constance. I'm a lecturer, I'm a staff engineer at the Technical University of Vienna. And I'm very lucky that I've been joined in my research by 3 master students that are currently finishing their CS degree. And yeah, at this point, huge shout out to the organizers for allowing this non-traditional change here and giving people a chance. And of course, the EU funding that is currently paying for all our infrastructure. With that said, this is offensive research. We have real clusters. They are really live. So anything is open source. You can replicate it, but please keep in mind, no liability. Be careful. And yeah, so originally we posted this and discussed it in the cloud native security community to solve the following problem. So assume you're in a pen test or a security review assessment, and you find 2 problems, 2 vulnerabilities. Vulnerability A has some score and maybe costs you a remediation of 10 units. Then you have vulnerability 2, costs you remediation of maybe 50 units. And you don't have time to fix both of them at once. How do you decide? How do you prioritize? And do we have a quantifiable means of figuring this out, fact-based? And this is where this idea came in. So the project's very young. We're about 10 weeks into the implementation, maybe 12 weeks now. And now I want to show you the setup of the first set of experiments, how we're doing them. We're not going to show you the actual attacks because they're live. If you want to find out, because it's a publicly recorded talk, talk to us. We'll show you some synthetic attacks. So that, for example, Josef is going to show you a realistic but synthetic attack exactly in detail how you would see it and what exactly you can see along such an arm, such an attack branch. Then Tobias is going to show you what you actually have to do to the cluster in the first place to make it see things. And in the end, Lucas is going to talk about how this is actually shareable, what standards we're basing this on, such that I can claim, well, if I see it and I give it to you, you actually get insights out of it. So this is the original talk. Recap is what our premises are. It's supposed to be simple, explainable, shareable, free, and transferable. And it's based loosely on the SANS Internet Storm Center. And yeah, we have our 4-fold path to threat intelligence. Right. Because the question is like, what are you afraid of? And the sometimes more important question is, can you actually reason and quantify why you're afraid of this? I think in the community currently we have sort of 3 big fears. One is the real breaches that happen. 2 days ago, what is the new OpenSSH 9-point-something vulnerability that comes out? We have gazillions of alerts in our dashboards and don't know what to do with them. Then we have vendors that exploit that fear and confusion by selling you silver bullets. that's something that, yeah, I'm not a particular fan of. And then we have regulations, our governing bodies, that are threatening companies, especially small companies, with big penalties. And I don't think that either of these things make software more secure. I think to become more secure is a bit like diet. Earlier we had a discussion. Like if you want to go on a consistent diet, you have to do something sustainable, achievable, that you actually can keep doing over a long period of time. And for that, it has to be, to some extent, easy as security could ever be. Now, it's not like there's nothing out there. We have a lot of really, really valuable information. We have blogs. Wiz has now this threat intelligence database, breach database. The problem, I think, at the moment is that whenever we translate it to our environment, it's still very bespoke analysis because we need context and security, right? Across the stack and across time. And that currently, especially because we can't build it on top of each other, makes it expensive. This is why we wanted to introduce something as a methodology based on open source, where we can make this a practice. Threat modeling is a practice, also detection response is a practice, so we can, like we do anything in DevOps, as a continuous improvement practice as a team sport. That's the idea. So what does it look like in real life? Typically, we know that our cluster, on the defensive side, we know that our clusters have some issues. And we are afraid of some things. But now assume you could take a safe system on which you could model some of those fears that you have. A realistic one could be credential leak into GitHub or into a Docker image, wherever not. I think it happens all the time. So, but now let's say we just model this and we see how fast does it happen? Does it actually happen? And does the impact that we thought it was going to have on our system match what is happening? And can we detect it? So those are the big questions to answer. And now, how do we currently offer or think about making the setup in the basics? So creating a honey cluster means you take your production system, you take the sensitive data out, you shrink it as much as possible. Well, this depends on your cost sensitivity. And then you put some instrumentation on it in the first place to get the events out. For this, we currently leverage Tetragon. This is simply to make it as user-friendly as possible to avoid you compiling eBPF code. So you can copy-paste our tracing policies to start with. We hope we can collect, and I think some companies are working on this anyway, many sample tracing policies for the OWASP top 10 cloud-native problems out there. And so you can get your cluster to emit the events that you are actually looking for. Now, if you want to set up the entire experiment, so you say, OK, I have fear number A, fear number B. You can model them on the same cluster, on a different cluster, and you put them out there. First of all, maybe only to your purple team. Maybe you say, OK, I'm going to write an attack and check if I can actually see what I expected to see, my exploit actually works. And then we have the other side, the other team that works on, all right, so now we see the events coming in, how can we map them into a benign versus malicious events and put them into a database where we can visualize it such that a human can actually see it and easily understand it and be in a standard that we can share. So the way we're currently exposing these experiments is we're focusing on data plane exploits, so purely attacks from application side, to guide the attack, so we can start with our parameter space being small. So down here, we have first off ourselves as attackers, so to validate. Then we put some baits out there. Those are CVEs that are well known. Then we put our instrumented honey clusters, and we've got some streaming and log processing in order to, in the end, get to our standard data model that is based on an old standard in threat intelligence is called STIX. And yeah, the way it works, you arm your cluster, you calibrate, validate, and then depending on your risk appetite, you actually put it into the wild and let actual attackers attack you. But for that, you obviously need to have some response in place as well. Maybe you don't want to start there. Right. So when we read these threat models, just in case you are not familiar with them, you read them from the bottom up. And what we keep in our current experiments constant is this initial access. Initial access currently is a remote code execution through our application vulnerability. We take high-profile ones, and we combine it with a service account that has the RBAC to be allowed to create a pod. And that's afterwards is actually where our experiment starts. So what do they do afterwards? How do they achieve command and control, and how do they achieve their objectives afterwards? Basically, the kill chain, how is it executed, and what can we see? We've loosely based our model, this generic threat model, on the 2021 Hildegard coin miner, which we believe we could see in this setup. However, this was based on the unauthenticated kubelet, which I think is completely reckless to run as a honey cluster, which is why we use a Java application RCE that allows us remote code execution, combined with leaky vessel that allows the attacker privilege escalation. And now, Josef, so what would we actually exactly see along this path of the attack? Can you show us?
Yeah, Constanze, we actually see balls, colorful balls. What are these balls? Yeah, these balls are actually stick objects. As Constanze has mentioned before, sticks is a standard language for modeling cyber threat intelligence. But let's deep dive into these whole balls and colors. Yeah, so let's start with a question: how do we take an attack? So in order to take an attack, we first, or you first, have to decide which attack you're interested in detecting. So maybe you are interested in some privileged escapes or whatever attack is currently into your mind. And for that, you have to model this attack. And for this, we use the blue balls, which are sticks objects describing the attack steps. So in this example, we see the first attack step of this whole attack performing a remote code execution. Now that you have your attack, the next step is to add indicators to it that are those orange balls. And yeah, they are actually pretty important because they are one of the main mechanisms for the detection. And yeah, let's have a closer look at one of these indicators. Indicators contains patterns, and in this specific example, the pattern basically says, okay, if you have some events that contains a file which name matches run secret Kubernetes IO service account, then label it as malicious and associate it with the attack step perform RCE. And mentioning events, we are collecting different types of events, from eBPF traces to app logs and network logs. And here we can see an eBPF trace. And what we do with that, we translate them into more colored balls. Yeah, and we are actually working with the sticks observables, that's how we call them, which actually are just an abstract representation of the different types of events. Yeah, enough of all this ball science. Maybe we can switch to an actual demonstration on how to detect a leaky vessel no takeover attack, which yeah, which is basically, or let me explain what this attack does. So we start with an initial point of access, as mentioned, as Constanze said, by having some vulnerable Java application that enables RCE, and some service account that has an airbag that let us create a pod. By using this, we create a weapon pod, which contains leaky vessel exploit. And what is leaky vessel? Leaky vessel is a vulnerability that enables attackers to run code as a root in a node from a container. So yeah, using an older version of run C. And by using leaky vessel, we are able to write some code in the node's cron tab, which then get executed by the cron-d service on the node, which establishes an reverse shell on the Kubernetes node. And yeah, having basically root access on a Kubernetes node. And so maybe I will switch to the laptop. Yeah. So the first step is, again, we have to write the whole attack as an attack model, add some indicators which help us identify the events that are related to this attack. And here, oops, that's not what I wanted to. Yeah. No, it's okay. Yeah, so we have this JSON here, which contains all the sticks attack model and sticks indicators. We upload them into a threat intelligence database on the Honey clusters, and by that, we then can see in the threat intelligence database, which is basically a graph database, that we have deployed this attack model and the indicators on the Honey cluster. From this point on, there is a matcher, which is basically just a process on the Honey cluster that does two tasks. The first one is to translate all the events on the Honey cluster to sticks observables, and the second task is to identify if one of these observables matches any indicators. By this step, we have armed the alarm of the Honey cluster, and the Honey cluster is carefully looking for this specific leaky vessel node attack. The second step would be performing the attack. Here we have two options. You wait till you get attacked, which will probably take some time, or you attack yourself, which I have done here. I'm running a script which basically performs this whole leaky vessel attack, and on your left, you see that, yeah, it was pretty fast, but you see that we have gained reverse shell root access on a Kubernetes node. Wait. Ta-da! Game over. Yeah. Now that we have performed the attack, we now can look into the threat database and see what our detector has collected. And yeah, let's see if it has detected this attack. Yeah, so now we, well, can you read this? I don't think so. Yeah, we have here these yellow balls, which are the indicators, and we can now see that the first indicator has two observables identified, and if we have a closer look, we can see that one of these observables describes a Java binary that basically uses the service account token, which is pretty suspect. That's the point where we actually created the pod. And the other observable he has identified is yeah, accessing basically the service account certificate. And yeah, so that's the first step. On the next attack step, which is basically the leaky vessel, he has identified an observable which shows us that he has done some stuff on the cron tab with by injecting this code here. You can see on the right, basically piping some cron job with some GitHub code that contains reverse shell code and piping it into cron tab. Yeah. Then we go over to the next step, which detects the execution of the reverse shell. before that, the execution of the cron tab by cronD. You can here see that the cronD binary has been started and that the reverse shell has been executed. And the final observable identified that we have created a TCP connect, which established the reverse shell via a pseudo device. Yeah. And
so thank you, Yusuf. So now Yusuf has shown you how you can arm the alarm system and how you're able to detect attacks happening. And now I want to show you how you can make your cluster attractive to attackers and make them want to bite the bait, and how you go from a bait to an attack model. So that does not work. Okay, so we want to model different kinds of mishaps, and it's important to choose the right bait in order to make attackers want to come to your cluster. And for that, we for now focus on RCEs, which are easy to instrument and have a clear attack path, and that we truly can understand, so we don't miss anything. And we focus on gaining access to the Kubernetes cluster, and for now, we want to see data plane attacks. But in the next phase of our experiment, we also want to look at control plane attacks to detect, for example, something like credential leaks. And so I prepared a small synthetic example on how you can find a vulnerability, which is ideally a well-known vulnerability where you know that it is being actively attacked. Yeah, probably. So now it works. All right. So for this example, we used a WordPress vulnerability, which has been a lot in the news and for which we can assume that a lot of attackers know about. And it's always good to have some POC exploits. So we know how to attack it, and also we know that attackers know how to attack it. And yeah, so I prepared a beautiful website for you, which is the basic WordPress example. And this is vulnerable to a file upload, which anyone can upload, a PHP file, and by that execute arbitrary code on the WordPress server. And we use that when I execute the attack, to download a kubectl binary and execute a vicious attack, which just lists all the pods on the cluster. And now how can we detect an attack like this and form a proper attack model? So for that, we have to look into the logs, what events actually look like during an attack. And for that, we first took a look at this kubectl execution, which we know we did. And we see that we can indeed see the attack, and we can see that it has been initiated by a shell call. And from that on, we want to find out where this shell call comes from. So we search for this shell execution, and we see that it has been initiated by the WordPress HTTP daemon. And now my idea seeing that was that, OK, every time WordPress HTTP daemon forks a shell call, we have something that is an entry point of an attacker. So I wrote a query for that, and I saw that there are also benign logs in there. There is an expected call to send mail. So it would be a good idea to exclude that, so we know that every time we see something here, this really indicates an attack. And with that, we can write an indicator, which is this orange ball you've seen earlier. And it consists of a pattern. And this is an example on how you can write a simple pattern to detect the entry point of an attacker using this vulnerability. Here we first match for a process which originated from the HTTP daemon. And it is a shell call, but it is not the benign send mail shell call we saw earlier. And now we have modeled the entry point of an attacker. And we can do the same steps to build more and more steps in our attack path until we modeled our entire attack path. So now I've done all this work, and it's really great. I see that it works, and I can see my own attacks. But it would be awful if you had to do all this again yourself, Lucas, wouldn't it?
Yeah.
Yeah. Is there any way I can share this with you?
Fortunately, I've prepared something for that. So now that we know how it works, we will now also want to share it. To make all that stuff shareable, remember, we are basically just collecting logs and doing something with it so that we get some balls out of it, right? This was pretty much the talk for now. So we need some specification for that to use some standards so other people know how what we mean by our balls, right? So everyone uses the same balls pretty much. And yeah, that's why we use an ontology for that, sticks. So now for the special effect, maybe with a small hint, can you guess who created it? So, who created it? Does anyone know?
The artist?
Artist, yeah. Oasis, yeah. So, yeah, exactly. So we use sticks by Oasis, and to then collect all those logs here and convert them to observables. One example you have already seen, and once we have those logs converted to observables, we can use our sticks indicators. Remember, the sticks indicators contain all the patterns we use to match those observables with the indicator, so that then we know, okay, this is now potentially malicious, right? If we find some match, we then save it in our thread database, pretty much. Now that we have our standard, remember, sticks is just JSON, so you can easily share it, right? And we have in our information from those sticks entities which attacks are currently happening. The more clusters we have, of course, the more we know, okay, those are attacked with that attack. So we know which attacks are currently trending, and this is open source information then. We, of course, then also know the attack details because we modeled our attack paths, right? And the best part about that is, as we already modeled it in sticks, we don't need any additional system information of that cluster that was exploited. And this is, all this combined is public intelligence that's currently rare. So now that you've seen how it works, how it is shareable, you probably also want to do it yourself, right? And those are the two main things you have to do to make it work in your environment. You need to adapt and probably create some indicators and tracing policies. We already provide some, but you probably in your own environment, maybe you need to modify some of them. And if you have done that work, we would be very grateful if you also share it with our repository so we can grow as a community and find more and more threads. But you don't need to take our word for it. You can, of course, try it yourself. Just go to our repo, scroll a bit down, and then you'll find how you can tailor those logs for you, for your cluster, that it works on your environment. So we have only one problem. We are not an interesting target. We are not a big company. We are not working in critical infrastructure. So if someone of you has some clusters lying around and wants to contribute, yeah, I know, it would be really helpful for the project, because then we can really see how those attackers attack attractive clusters. Yeah, of course, interesting would be, of course, financials, telcos, government, military, so all the interesting targets, pretty much. If you want to collaborate, we have models in different legal setups depending on your requirements and your legal department. So what we also need, probably you've seen it already, on our WordPress site, it's not really that big, right? And it's not really convincing. So if you have some closer to real life bait, we would be also very grateful if you could share that. So we all are probably afraid of some things. Security is hard, right? You see, all those vulnerabilities that get there. And with our project, we try to track those guys, what they are up to, and instead of doing the cycle again and again. So this is how a honey cluster could benefit you pretty much. Because we provide with that honey cluster a hands-on environment for gathering threat intelligence. You can see for yourself, can you exploit yourself? If you can exploit yourself, okay, are those baits or pretty much the vulnerabilities you set up yourself are really as bad as you have feared all the time? And once you have done, if you already exploited yourself, you probably and hopefully have seen that your detection and response kicks in as you had planned all the time. But you probably never have seen it as you didn't try it yourself, right? And that's the perfect training to train yourself for NIST 2. And, of course, what I've learned in the past few months working on the project is to do threat intelligence, it really takes some balls. The only question left is, do you have what it takes? Thank you very much.
So first of all, thank you for this very interesting talk. That was a really an interesting way to look at the overall landscape and what we can do about it. So in this concept, we are kind of looking at, what do you call this, signals or indicators, right, of something what had happened. My first question is, how do we actually then tie this back to a CVE? So is it, for example, of the observation you have shared, it may have been the CVE you were showing, leaky vessel, or it could also have been a different one, right? So what is the probability that we are actually able to tie this back to a known or maybe unknown CVE? Which comes to a second question. So we don't know what we don't know, right? So how would that system help to identify things we don't know yet?
Right, so if I may take that. So we also currently, of course, have exactly that problem, right? We have 6 attack paths that we currently got modeled out. So most of it falls in the unknown bucket. So we do have a central database at the moment in MongoDB where we just collect all of it and do basically explorative analysis and try to build more and more and more of these matching patterns. However, the exact statistic of whether that is exactly that CVE remains always the context, right, that you have to do as an analyst. There's always going to be some room for doubt. And yeah, you can basically assign a probability to it. Yeah. In this case, this is why we chose these exact RCEs and not pretty much else, right, to have a clear attack path to guide it in and then to see what happens. Yeah, I hope there is no silver bullet. We're not promising that right now.
Thank you for this. Very interesting, very funny. What was the most fun part on developing it, and what was the hardest part?
The most fun part, if I say so myself, was when we were creating it, we didn't have that graph database. So we worked for weeks with just JSON logs. It was crazy, and this was also maybe the hardest part, at least for me. And when we finally got the connection to the graph database working and seeing those balls, we were really, really happy, because that makes it so much easier.
Thank you.
Yeah, thanks also from my side. It's very interesting. Have you plans on integrating the stuff that you now build into the Sigma project as well, which would make the whole detection part actionable for a lot of security teams all over the globe?
For now, not. I mean, I think I said it's like we're like 10 or 12 weeks into the implementation, collecting a lot, looking around what other people, what other groups are doing. We're very, very happy to share and like what makes sense is the next step. So anything that is reusable is potentially the best thing, because that's exactly the goal, right? To make it as reusable by all existing standards that are actually used by the community. So happy to hear more about it.
Okay, thank you.
Regarding your honeypots and everything which you need, come downstairs, we'll organize something. Okay, and then we can look into sharing data and expanding it a bit more. Yeah, definitely, yeah.
Thank you. Fantastic. Thank you so much for attending.